Hello everyone, my name is Serhan Gül. I'm a researcher at Fraunhofer HHI at the Video Coding and Analytics Department. In this talk, I would like to present our NOSSDAV paper with the title Low Latency Cloud-Based Volumetric Video Streaming Using Head Motion Prediction. This is my joint work with Dimitri Podborski, Thomas Buchholz, Thomas Schiel, and Cornelius Helge. First, let's talk about what a volumetric video is and which content formats can be used to represent it. Volumetric video is a technique that captures the 3D space and objects from all viewing directions. In other words, it allows us to watch a video in 6 degrees of freedom, such that we can walk around an object or approach to and move away from an object. This allows novel mixed reality applications where highly realistic virtual objects can be overlaid on top of real environments and viewed with a high degree of immersion. Depending on the capturing technique, a volumetric video can be represented as point clouds or meshes. For both types of representations, there exist different workflows for storage and processing of the content. As you see in the picture, we use a mesh-based workflow and represent the texture map as a video stream. We then render the mesh geometry and the video-based texture together in a synchronized way and obtain a volumetric video that can be viewed from any viewpoint depending on the user interaction. So let's go into a little bit more detail about the storage of mesh-based volumetric videos. How can we store the volumetric content in an efficient way and prepare it for streaming? As you see in this diagram, we compress the texture and mesh data separately. We compress the texture using H.264 and meshes using the Draka software by Google, which implements a widely used mesh compression algorithm called Edgebreaker. After compression, we multiplex the coded data streams into an MP4 file as separate tracks. And the created volumetric asset is then ready for storage and streaming at a content server. However, streaming volumetric content and processing on the client side, which is typically a mobile device, can be very challenging for a number of reasons. First of all, high-quality mesh representations can have tens of thousands of polygons, and if we consider that typically we want to stream multiple volumetric objects, we simply don't have enough processing power on mobile devices for that. Also, there are no efficient hardware decoders available in mobile devices yet for decoding volumetric content. Software-based decoding it's an option, but it can be very expensive in terms of battery usage. It may also not be able to meet the real-time rendering requirements. Another aspect is the high bitrate of the volumetric content. If we consider that even a single high-quality volumetric object can easily require multiple tens of megabits per second for streaming, we can see that streaming a complex scene can easily be a huge challenge on even high bitrate networks. So how can we mitigate these issues? A potential solution to alleviate the issues that I just mentioned is to offload the rendering of volumetric video to a powerful cloud server and send a rendered 2D video to the client device. In short, we call this approach cloud-based rendering. So let's look into how cloud-based rendering works. So as you see in the diagram, we have an AR client which is shown here as a smartphone, but it doesn't have to be a smartphone. It's typically an AR glasses like Microsoft HoloLens. And based on the user interactions, such as changing the viewport or moving virtual objects or controlling playback, the AR client sends control data to the cloud server, which then does the processing of the volumetric video. This is basically demultiplexing of the MP4 file, decoding the individual data streams, rendering them, also for multiple objects, different video streams. And this rendering is controlled based on the user input, and the 2D rendered view is encoded. which is then streamed to the AR client. And this 2D view is dynamically updated based on the user interaction. So let's take a look at the components of our system architecture in more detail. On the cloud server side, we have two main building blocks: a volumetric video player and the cloud rendering library. The volumetric video player is a Unity application that plays the volumetric asset by demultiplexing the MP4 file and pushing the data into the integrated mesh and video decoders, and then does the rendering. The cloud rendering library, it's basically an SDK that we wrote in C++ and integrated into the volumetric player as a native Unity plugin. It has many different components like a WebSocket server, GStreamer media pipeline, a prediction engine, and a controller. So basically, the library provides the interfaces for registering the objects of the rendered scene and retrieve the latest client-controlled transformations of those objects while rendering the scene. The WebSocket server is used for exchanging the signaling data between the client and server. The signaling includes SDP and ICE, as well as application-specific metadata for scene description. Also, the WebSocket connection can be used for sending the control data, for example, changing the position and orientation of any registered game object or virtual camera. There is also a GStreamer module that contains the whole media processing pipeline, which takes the rendered texture and compresses it into a video stream, which is then sent to the client using the GStreamer WebRTC plugin. And there's a controller module, which basically represents the application logic and manages the other modules depending on the application state. For example, it closes the media pipeline if a client disconnects, or reinitializes the media pipeline when a new client has connected. It can also update the controllable objects based on the output from prediction engine. And the prediction engine, it implements a predictor, in this case an autoregression based prediction method, which I will explain in the next slides. And it also provides interfaces for integration of other kind of predictors. So based on the previously received input from the client, the controller updates the position of the registered objects such that the rendered scene corresponds to the predicted positions of the object for a given prediction time or a look-ahead time. And this is the server. If we look at the client, we can see that the client is much simpler. So basically, before the streaming session starts, the client establishes WebSocket connection to the server and asks the server to send a description of the rendered scene. The server then sends a list of objects and parameters which can then be updated by the client. And after receiving the scene description, the client replicates the scene and starts a peer-to-peer WebRTC connection to the server. And there's a WebRTC negotiation process by sending SDP and ICE data over the established WebSocket connection. And after the connection is established, the client starts receiving a video stream corresponding to the current or predicted view of the volumetric video. At the same time, the client can use either the WebSocket or the RTC peer connection for sending control data to the server in order to modify the properties of the scene. For example, the client may change its sixth of position, or it may rotate, move, or scale any volumetric object in the scene. Yeah. So this is the operation of our system basically. So despite its advantages in terms of rendering complexity and streaming, cloud-based rendering comes with a price, which is an increased interaction latency, or also known as motion-to-photon latency. In the figure, we should see a breakdown of the motion-to-photon latency, the different latencies on the server and client side corresponding to the network, rendering, encoding, decoding, and display latencies. If you look at what kind of optimizations can be done and what techniques can be used to reduce this latency, we see that there are a number of options. First option is hardware video encoding, which is necessary to keep the encoding delay to a minimum. In our system, we use NVIDIA GPU-based encoders based on an analysis of encoder delays that we present in our paper. Secondly, usage of RTP-based low-latency streaming protocol like WebRTC is very important. We use that in our system. Thirdly, we all know that 5G is reducing the latencies in general, and we also use an edge server to further decrease the latency in our system. The next point is the prediction of the user's sixth of head motion, which we investigate in our paper. This can completely eliminate the motion-to-photon latency if the prediction is performed with a high degree of accuracy. And lastly, on the client side, post-rendering correction can correct the errors that occur after the prediction. So these techniques are commonly known in the VR world as time warping, and Microsoft HoloLens calls them late-stage reprojection, but the fundamentals are the same. So in summary, in our system, we already employ the first 3 bullet points in this list. Post-rendering correction is performed by the client device. And in the next slide, we focus on the head motion prediction and the technique that we propose for integration in our system. We use an autoregression model to predict the future values of the head position and orientation of the user for a given look at time. We developed our predictor based on the head motion traces collected while interacting with a virtual object overlaid on the real world. From Microsoft HoloLens, we obtained the position and orientation data and recorded 5 traces, one of which we used as training data for our autoregression model to create 2 different models for translational and rotational components. So basically, we predict the next sample using an automatically detected history window of the past 32 samples, which corresponds to 160 milliseconds with a sampling time of 5 milliseconds in our system. So the equation shows how the model works. So phi i's are the model coefficients and xi's are the lagged values of the time series. It can be x, y, z, or the different quaternion components of the orientation. And then we iterate this equation to perform multi-step prediction as shown in the figure below for an example history window of 3 and a prediction window of 2. So we repeat this equation multiple times to predict multiple steps ahead. And these are our results, where we perform the prediction separately on x, y, z and different quaternion components. For the evaluation, we converted the quaternions to Euler angles. We plotted the mean absolute error for all components averaged over 5 users for different lookup times between 20 and 100 milliseconds. For all components, we see that the developed autoregression model has a better performance than a baseline model where we don't do any prediction. So this seems to work over all dimensions and brings certain advantages for both translational and rotational components. So as a conclusion, to summarize, we developed a cloud-based volumetric streaming system that reduces the rendering load on the client side, and we compensate the increased system latency due to cloud-based rendering using head motion prediction. And our results show that the autoregression model reduces rendering errors caused by the added latency. In our future work, we want to analyze the effect of motion-to-photon latency on the user experience through subjective tests and develop more advanced prediction techniques, for example, based on Kalman filtering. And this concludes my presentation. Thanks a lot for listening.